So Kirchhoff's current law states that the algebraic sum of all currents entering and exiting a node or a wire junction is 0. So that means that just algebraically we have the current flowing in is going to be equal to the current flowing out of a junction. Or we can also state that as it's like the algebraic sum of all currents at a point is going to be equal to 0. So if we just draw a junction where we have 3 wires connecting, so we have 1, 2, and 3, and let's draw on some currents. Let's say we have one flowing in, one flowing out, and another one going like this. So if we give them names, let's say we have I1, I2, and I3, then in order to get our expression like this, what we do is we pick a direction to be positive and we pick another direction to be negative. So let's pick a current flowing out to be positive. So then we can write our expression summing to 0. So we have I3 plus I2. So these are both positive because they flow out. And then I1 flows in, so we're going to give it a negative value in the sum. So we have minus I1 is equal to 0. We could rearrange this as well. We could bring the I1 to the other side, and we could have just I3 plus I2 is equal to I1. That would be the currents flowing out are equal to the currents flowing in. Or we can write it with them all on one side, picking the direction of positive being outwards and negative being inwards. Okay, let's give some of these some values. So let's say that I1 is equal to 9.75 amps. And let's say that we know I3 is 4.5 amps. Then the question would be, what is I2? Well, we can just fill in the values that we have. We know that I3 is 4.5 amps. I2 is a big mystery, and we have to subtract I1, which is 9.75 amps, set that equal to 0. We can just rearrange this, so bring 9.75 to the other side and subtract 4.5, and we're going to find that I2 is equal to 5.25 amps. Now, this is a positive value, so this means that it is indeed going in the direction that we assumed when we just arbitrarily labeled it on as leaving the junction. If we got this as a negative value, it would just mean that the current is actually flowing the other way. All right, let's draw another slightly more complicated example of a wire node. Let's say we have 5 wires connecting at one point. And often with problems like this, you'll be given some information. So let's say we have the currents like this, and we're going to be given 3 of them. So let's say that I1 is 3 amps. Let's say that I3 is 11 amps. I5 is 4 amps. And I4 and I2, let's leave them being unknown, but we'll say that I2 is equal to 3 times I4. So what we need to do to solve this problem is set it so everything sums to 0, and let's pick inward currents as negative and outward currents as positive. So we can write our expression. We have negative I1 plus I2. No, I1 is negative because it flows in. I2 is going to be positive because it flows out. We're going to label on I3 as positive because it flows out. Same with I4. And then I5 will be negative because it is flowing in. And we'll set that all equal to 0. Okay, we know some of the values. So I1 is negative 3 amps. I2 is positive, but it's going to be equal to 3 I4. So let's put that in now. I3 is positive 11 amps. I4 is unknown, so we'll just leave it as is. And I5 was given its negative 4 amps, and that's equal to 0. So we can simplify a little bit. We have 3 I4 plus 1 I4. That gives us a total of 4 I4. And then we have 11 amps minus 4 amps minus 3 amps for a total of 4 amps as well. So that is plus 4 amps, and that is equal to 0. Well, we can just rearrange that, so we have I4 is equal to 4 amps over 4, which means that I4 is just going to be equal to negative 1 amp. Then what we can do is we can plug this into our expression for I2. So we had I2 is equal to 3 times I4, which means that I2 is equal to 3 times negative 1 amp, and I2 is ultimately equal to negative 3 amps. And for both of these, the negative signs indicate that they're actually flowing in. It's opposite to the direction that we assumed here when they were unknown. So what we could do is we could update the arrows here, just like this, and turn them facing inwards. Or to make it even more clear, we could even change the color that we've updated it. And then when we label on the actual current, we could say that it is positive 3 amps flowing in and positive 1 amp flowing in. Or if you left the arrows pointing out of the node, you would have to leave the value as negative. Either of those would be totally fine, because either way it is basically just indicating that the sum is equal to 0. And you can even look at it here. If we have 3 flowing in plus 4 plus 1 plus 3, so we have 6, 10, 11 amps flowing in, and then 11 amps flowing out. So in is equal to out, or the sum of all of them is equal to 0. All right, that's enough for the introduction to Kirchhoff's current law. And join me in the next video, and I'll go over another example that's using an actual circuit instead of just a wire junction.